Generalized linear models for counts using Navure. Part 1. To illustrate this procedure, we will use the test data named mites. Locate this file in the test data repository. It contains the counts of adult mites growing in a chayote crop. This data is from a mite control trial. The treatments were ACMC, acaricide and mechanical control defoliation, ACNM, acaricide and no mechanical control, NAMC, no acaricide and mechanical control, NANM, no acaricide and no mechanical control. The response variable was the number of adult mites per sample unit. Counts were conducted for 7 consecutive months. Each treatment was replicated 4 times in a complete block design. Mean temperature records were also available for each plot in each sampling instance. Just for exploratory analysis, we'll plot the average number of adults by months. To do this, we click on the Graphic tab, and then on the Dots button, select the column of adults as the y-axis and the month column as the x-axis, and click the blue play arrow. It is clear that average population growth until July and then begins to decay. These data are called longitudinal because the same plot was observed several times over time. In this video, Part 1, we will ignore the problem of longitudinal data and compare treatments during July. In another video, Generalized linear models of counts using Navure Part 2, we will do a more comprehensive analysis, including all months. Now let's go back to the data, find the month column, and filter the month of July. The model that we will fit will include the effective treatment and the effective blocks. Since the response variable is a count, specific models can be applied. Now we will fit a generalized linear model for counts. Click the Univariate tab and then click the GLMM button. In the dialog box that appears, select adults as the response variable and treatment and block as the class factors. Note that you can also include a covariate. At the top of the dialog box is a field called offset, which we will refer to later in the text. Click the blue play button to start the process. A new dialog box appears, with a navigation pane on the left containing 5 items. Each item presents different options in the middle pane, while the right pane displays the previously selected list of factors and covariates. First, examine the contents of the Fixed Terms tab. This tab has 2 panes in the middle, Family Options and Fixed Terms. The response variable in a data set is typically a mixture of random variables that belong to the same family but differ in the parameters that characterize them. For example, suppose we have a data set from a 1-factor, 3-treatment experiment in a completely randomized design. When we say that the response variable is a normal random variable, this is true only if the mean and variance are not changed by the treatments. Technically, it is more accurate to say that the response variable is a mixture of random variables that all belong to the same family, say normal. This is what the Family Options panel refers to. The default family is set to normal, which assumes that the response variable is a mixture of normal random variables with the same variance. If the variable in question is a count, it is more appropriate to select the Poisson or negative binomial families. We will select Poisson. Note that this choice will cause 2 fields to appear, namely offset and link function. But what are these options for? Consider a scenario where the number of adult mites is determined by examining different numbers of plants in each plot. In such cases, a direct analysis of the count is incorrect, because the number of adults depends not only on the treatment but also on the sampling effort. The analysis should then focus not on the raw counts, but on counts per plant. This is where offset comes in. If the counts were made on different numbers of plants, a new column in the data set, say plants, must be created that contains the number of plants examined per plot. Declare this variable as the offset in the initial dialog. The offset field in the current dialog will display the variable name of the declared offset, such as plants. The link function is not an easy concept to explain in a paragraph. But it establishes the relationship between the expected value of the response variable and the so-called linear predictor, thereby accounting for nonlinearity and ensuring that the estimates of the expected values and their confidence intervals will be in the range of the random variable. For example, in a Poisson model, the link function is the logarithm of the expected counts. When you estimate the model, the estimated expected values are on what we call the link function scale. On that scale, the expected values and predictions will be in the real number range, but when we go back to what we call the response scale, which is what we use to report results, they will be in the range of a count. No one will be less than 0. Let's shift our focus to fixed terms. Our primary interest is the comparison of treatment means. To do this, either double-click the treatment item in the right pane, or drag and drop it into the fixed terms pane. While our focus is on the treatment, it's important to recognize that the block can also contribute to variation. The complete randomized block design is used to proactively identify potential sources of variation in response variables. For example, we can consider different sites as blocks, each with different levels of mite populations. Although the difference between blocks is not our primary interest, it is important to recognize it as a source of random variation. Therefore, we'll label it as a random term. To do this, navigate to Random Terms in the left pane and double-click Block in the right list to add it to the random terms. Assuming the model is satisfactory, proceed to request a post hoc multiple comparison of means. Click Post hoc Comparisons in the left pane and select Treatment from the list of fixed classification terms. Select from several post hoc comparison methods. We'll stick with the default method, DGC, because it prevents overlapping of mean groups. Finally, click the OK button to continue. Let's explore the output. Below the model title is the R script for fitting the model. If the column names involved in the model contain non-ASCII symbols, note that they have been changed in the script to contain only ASCII symbols. The model summary table provides an overview of the conditions under which the model was fitted and includes key statistics for model comparison, such as AIC and BIC. It also presents the deviance, an important metric that indicates the fit of the model to the data. This metric, when divided by the residual degrees of freedom, df, of the model, serves as an indicator. Ideally, this ratio should be around 1 for a well-fitted model. A problem arises when the ratio exceeds 1, indicating a phenomenon known as overdispersion. The question then becomes, at what point does the ratio become problematic? While the answer is somewhat subjective, we contend that a ratio greater than 2 should raise concerns, and if it exceeds 3.5, it indicates a clear problem with the model fit. The ratio of deviance to residual degrees of freedom in our example is approximately 7, which is too high. This indicates that our model is overly optimistic, suggesting more accuracy in its results than is warranted. If you look at the last column of the mean comparisons table, where different letters indicate that treatment means are significantly different at the 5% significance level, all means are reported to be statistically different. Will these conclusions about mean differences persist if a better model, in the metric of deviance to degree of freedom ratio, is fitted? When a Poisson model shows overdispersion, the common solution is to fit a negative binomial model. To perform the fit, let's go back to the Univariate tab and click the GLMM button. All the settings from the first dialog are already set. Click on the blue play arrow. We only need to change the family option to negative binomial and click the OK button, since all other settings will remain the same. Now the deviance is 15.82 and df 10. Their ratio is about 1.6, below 2. So, we can assume that this model has fitted well. The ANOVA table says that there are significant differences between treatments. If we look at the means comparison table, the estimates mean of mites count per sampling unit are under the column mean and their standard error in the SE column. The last column of this table is the result of post hoc comparison of the means. The treatment means not sharing the same letter are declared to be significantly different. Compared with the previous model, in can't declare different the two treatments containing acaricide. A graphic representation of these results is shown below with a bar chart.